All right, so this is Minor Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and use school and participate fully, but do not share personal information during class for your own security reasons. All right, so let's go ahead and take a look at this. There's no brain stretch today because we do have an exam, so I want to make sure we have as much time as possible for that exam today. At this point, if you haven't already, again, make sure you have your attendance check open and ready to go. Your start of class word is underneath the link in the chat box. So make sure you have that filled out for today already. And then here is our schedule. So today we're taking a look at the Unit 3 and 4 exam. Yesterday there was a recording for Pascal's and Bernoulli's principles because unfortunately I was out of class yesterday for an urgent issue. So please make sure that you watch yesterday's recording because it is on today's exam as well. So if you feel confused about the last two questions on the exam, it's because you didn't watch yesterday's recording closely. So make sure you go back and watch that if you need to. Okay? All right, so we are talking today about Unit 3 application of forces and Unit 4 fluid forces. That's what our exam is going over. And today we should be able to explain the effects of friction and gravity, calculate net force on an object and describe the results, and explain freefall buoyancy and pressure and understand Bernoulli's principles and Pascal's principle, right? Which again, that was from yesterday's video. So if you don't feel comfortable with that, make sure you go back and watch that, all right? Oops, sorry. So let me go back to this. So at this point, what I want you to do is you can go ahead and open up your exam if you want to. Again, I generally recommend on exam days, don't open your exam because this way it's easier to follow along. You're not going to have time to actually answer all of the questions because we're going to go quickly. So really what I recommend is just to take pictures and screenshots. Give me a smiley face if that makes sense. So either have the exam open or be ready to take pictures and screenshots. Again, I highly recommend just take pictures. Just take pictures. Good. All right. So I'll send that out one more time. Looking good. All right. And if you're watching the recording, it's in the content tab. Go down to Unit 4 on the left, and then you should find 4D exam. That's what we're working on today. All right, so here we go. This is just like our last exam. So what's really important to understand here is as long as you complete a valid attempt on every question, you will automatically get a 50%. So valid attempt means that you try to answer it and you try to answer it with something that makes sense. All right, you don't just write gibberish or you don't just write I don't know or IDK or you don't just leave it blank. Okay, so as long as you fill in every single question, all right, to the best of your ability, you automatically get a 50% because my rubric is based out of 10, is a 5 to 10 rubric, all right, because it's based on letter grade. So 5 is F, 6 is D, 7 is C, 8 is B, 9 is A, 10 is A+. All right, give me a smiley face if that makes sense, everyone, okay? So just make sure you're answering every question to the best of your ability, and then it's graded on a 5 out of 10. If you leave it blank, you automatically get a 0 on that blank, okay? And it also goes in increasing levels. So question 1 is easy at developing. Question 2 is a little bit harder, foundational, all the way up to number 5, which is mastery for the first unit. And number 10 is mastery for the unit 4, okay? All right, so let's go ahead and keep on going. Oh, I do want to remind you, if you copy anything from the internet or from Google, this does result in immediate 0, and you will be referred to the administration for plagiarism, and you don't need to copy because everything's in this video or in this class or in this recording. So I give you everything, you don't need to copy anything, okay? All right, so the first thing that we're going to do is we're going to go ahead and take a look at question number 1, and question number 1 is about friction. So we want to define friction as we talked about it in class, and we want to know what's static friction versus what's kinetic friction. So go ahead in the chat box, tell me, what do you remember about friction? What do we know about friction? Tell me in the chat box. How did we define friction in class? We need lots of participation. If we don't get enough participation, we're not going to finish on time. So make sure you are participating in the chat box with everyone else. Tell me, what is friction? What does friction do to objects? Awesome, I see Lolo typing. I need way more participation in the chat box. Tell me what is happening with friction. Awesome, now I see Jones typing, I see Z typing. How are we defining friction in class? Holly typing. Yeah, it makes you not fall off of your seat, right? Friction is really useful, and how is it preventing you from falling off your seat? So it's a force, right? So we know it's a force. What else do we know about it? It's a force. I often called it a force that starts with an R, like prevents you from doing something, or R, what's that word that starts with an R? Yeah, so it slows things down, or what's another word for that? Starts with an R. Blank motion, starts with an R. Prevents or what? Tell me in the chat box, what's this word? Starts with an R. It means it's a word that's similar to meaning it prevents or tries to stop. What is that word? We are not going to get through the entire exam unless I get more participation, please. Close. So restricts is close, but really it's actually it resists. It resists motion. Smiley faces if that makes sense. So it actually resists or tries to prevent motion. Smiley faces if that makes sense. I know, it's a hard word. Perfect. Okay. So this right here, all I'm doing is I'm going to be writing notes up on the board. Do not copy the notes down, because if you copy the notes down, you get a 0 because it's not a complete sentence. So make sure you take all this information and you actually write it in a complete sentence. So you have sentence starters and you have the red blanks where you fill in the rest of the sentence, but make sure the rest of that sentence is a real sentence. Do not just copy force, slows, resists, because that's stupid and I won't know what that means in real life. Okay, so make sure you write a complete sentence. All right, so let's talk about static friction. Static friction versus kinetic friction. Which of these resists an object when it's staying at rest? Which one resists an object when it's staying at rest? Static or kinetic? Think about the word stay. Is that a static thing or a kinetic thing? The words look very similar. The word stay, what does that mean? So kinetic, you want to think about like kinesiology. In college, kinesiology is the study of motion, of the body's motion. So yeah, it's actually static. So the word static actually means it stays. This is like how static electricity stays in your hair. So if you think about the word static, this is very similar to the word stay. Smiley faces if that makes sense. So the word static is similar to the word stay. And so static friction works against an object when it's at rest, right? So if it's at rest, this is what's preventing you from moving it. So when you're trying to push a fridge or a dresser across the ground and it's refusing to move, it's not because you're weak, it's because static friction is working against you. I mean, it might be because you're weak, but for the most part, it means it's because static friction is working against you. What about kinetic friction? Kinetic friction works against an object that's what? Tell me in the chat box. Based on what we know, static means it's at rest. What about kinetic? What does kinetic mean? Yeah, kinetic means it's already moving, exactly. So kinetic friction means that the object is moving, okay? And so it's resisting it as it moves, and what's that going to do to the object's motion? Is it going to speed it up, keep it the same, slow it down? Tell me in the chat box. What happens to the object's motion then? Yes, Antonio. Do we agree? Yes, it's going to slow it down. Exactly. Slows it down. Awesome. Again, these are just notes. They are not the answers. You need to write these into complete sentences. And this, thank you, Jones. Yes, you're going to get 30 seconds to take a picture of this and give me a green check telling me you're ready to move on. Green checks. Go, go, go. All right, green checks, please. Amanda, Ayandela, Benjamin, Christian, Chloe, Kayla, Enrique, Irwin, Joe, Jaslyn, Kayla, Michael, Ray, Tatiana, Trenton, Z. Keep in mind, guys, we are doing an exam today, so I'm not going to be calling names out a whole bunch. And if you get left behind, you get left behind. So make sure you're paying attention, just because I want to make sure we get through everything, okay? It'll all be in the recording anyways, but make sure you are following along with us as we go. Perfect. All right, let's go ahead and keep on going. So question number 2 is talking about mass versus weight and explaining what the mass would be like on Earth, Moon, and outer space, and what a person's weight would be like on Earth and outer space. So tell me in the chat box, what is mass? Tell me in the chat box, what do we remember mass is? What do we remember mass is? I see Jones typing, I see Lolo typing. I need more answers. Alyssa and Amanda, Drea, Andrew, Antonio. No, it's not exactly the same thing as weight. Weight is different. That's why we're defining both mass and weight. Let's try to remember. What did I say mass was throughout class? We've talked about it about 10 times. What is mass? No, not exactly area. Area is the amount of space something takes up in a 2D surface. What is mass? I see Enrique. So it looks like we understand weight. So weight is the effect of gravity on you, right? So weight is due to the force of gravity on you, on your mass, right? But mass, no, mass and volume are not the same thing. So mass is actually the amount of matter or stuff that you're made of. Smiley faces if you guys remember that. So matter is the amount of stuff that you're made of or the matter that you're made of. Matter meaning atoms, molecules, particles that you are made up of. Awesome. Now weight on the other hand is the actual force due to gravity on that mass, right? So it's a gravity affecting that on that mass. Okay, so let's go ahead and think about how does mass change on the Earth, Moon, and in outer space? Remind me in the chat box, does the amount of stuff or matter or mass that you're made up of change whether you're on Earth, in the Moon, in outer space? Does your amount of stuff change? No, your amount of stuff does not change. So it doesn't change, right? It stays the same because your stuff stays the same, yeah? So the amount of stuff that you're made up of always stays the same. So that should not change. It should be equal no matter where you are in the universe. Okay, what about your weight? How does your weight change based on if you're on the Earth, the Moon, in outer space? Tell me in the chat box. How might our weight change? Yeah, it depends on gravity. So think about which one has a lot of gravity, Earth, Moon, or outer space. Which one has a lot of gravity? Yes, perfect. So the Earth has a lot of gravity, right? So Earth has lots of gravity. And so are you heavier or lighter on Earth? Are you heavier, lighter, or weightless on Earth? Yes, you are much, much heavier on Earth than, for example, the Moon, where there's less gravity, or outer space, where there's no gravity. So what you should be able to do is you should be able to analyze each of those. So I'm only showing you the Earth, but you should be able to, based on that, be able to figure out Moon and outer space as well. Smiley faces if you feel like you can do that. If you know how to do Earth, you should be able to figure out Moon and outer space as well. Smiley, smiley, smileys. Thank you, thank you, thank you. Perfect. All right, so this is number 2. Green checks when you have it saved. You have 30 seconds. Go. Lolo, I'm not on camera right now because I'm on a different computer and I just don't want it to lag too much. I am recording it with webcam though, so if you watch the recording, you'll see me. Cool. All right, everyone, let's keep going. I have 10 green checks. There are 40 of you, so make sure I'm getting green checks as we go, telling me that you've taken a picture of this. You're ready to move on. We're going to move on in 5 seconds. 5, 4, 3, 2, 1. Let's go. All right, so question number 3 is asking about Newton's third law of motion. So Newton's third law of motion is that for every action there is what? Tell me in the chat box. There is a blank and blank what? For every action there is a blank and blank what? Yes, there's a reaction, and that reaction is what and what? For every action there is a blank and blank reaction. There's an opposite as well as what? Starts with an E. There's a blank and opposite reaction. Yes, equal and opposite reaction. Exactly. So what this means in terms of forces is that for every force, there's an equal and opposite force. Smiley faces if that makes sense. Again, these are just notes, so make sure you write this out as a sentence and don't write this down word for word because it'll look stupid. So make sure you write it as a complete sentence, okay? All right, so Newton's third law, right? Every force has an equal and opposite force. So based on this, let's think about this. The Earth's gravitational force on the Moon versus the Moon's gravitational force on the Earth. So the Earth is pulling on the Moon, and the Moon is pulling on the Earth. And those pulling forces, are those the same or different based on Newton's third law? If every force has an equal and opposite force, are those forces, Earth on Moon and Moon on Earth, are those the same or different? Are those going to be the same amount or different amounts? No, they're not going to be different. They should actually be what? Again, we said equal forces. They're actually the same, all right? So we should be able to figure out that these are actually the same forces, right? So it's the same force, they're just in different directions, right? So the Earth is pulling one way, the Moon is pulling the opposite way, but the reality is they're actually pulling on each other with the same exact force. If it wasn't the same exact force, it would be like a tug of war, where if one of them was stronger, it would actually pull the Moon into the Earth, which would be bad. All right, so these are not these are not different forces. They're actually the same force. Smiley face if that makes sense. They have to be the same because Newton's third law says that they have to be the same. And again, the Moon would crash into the Earth if they weren't the same. Now, if this is true, though, the hard thing for us to think about is if this is true, then why does the Moon orbit in such a big circle while the Earth does not, right? The Earth just stays in place, or if you were to measure the Earth's rotational motion, it's actually kind of wobbling in place. So why is the Earth only wobbling while the Moon is orbiting in this giant circle? And this has to do with the main difference between the Moon and the Earth. Tell me in the chat box, if you were looking at a model of the Moon versus the Earth, what's the main thing that you would notice? What is the main difference between the Moon and the Earth? Yeah, one of them is really, really big. And if it's really, really big, does it have a lot of mass or a little bit of mass? Yeah, the Earth is super massive. So the Earth has lots of mass. So it has a big mass. And if the Earth has a big mass, tell me something that has a big mass. Think about like trying to move a fridge. All right, if you apply the same force to a giant big fridge versus a small light box, that giant fridge, is it going to be able to accelerate quickly or slowly? If I use the same force, because I am only so strong, is it going to accelerate quickly or slowly if it's really, really big and massive? Yeah, so because the Earth is such a big mass, it actually ends up with a very small acceleration. All right. So with a small acceleration, that means it's not going to go in a big circle, right? As opposed to the moon, which has a small mass and therefore should end up with a big acceleration. And so that one does spin in a very, very large circle. All right, give me a thumbs up if that makes sense. Again, if you should be able to explain the Earth as a big mass with a small acceleration, you should also be able to explain the moon. All right, so make sure you explain both of them. I'm not going to give you the answer because you should be able to figure it out on your own. All right, you have 30 seconds to get a picture of this slide and to give me a green check. Go. All right, I have 12 green checks. I have 12 green checks and 41 of you. Make sure I'm getting those green checks. Moving on in 5 seconds. Speak now, forever hold your peace. 3, 2, 1, here we go. All right, so question number 4 is asking about net force, all right? And this was actually what your entire lab was over, so this one should hopefully be pretty, sorry, Z. This one should be pretty familiar with this. So what this asks us to do is it asks us to calculate overall vertical force, overall horizontal force, and to describe the final net force on the object based on those vertical and horizontal overall forces, okay? So let's go ahead and work on this together. So 40 newtons going up, is that going to be positive or negative? Tell me in the chat box, is that going to be positive or negative? If we have 40 newtons going up? If it's going up, think about upwards. Yeah, that should be positive. So 40 newtons going up is actually positive. What about 100 newtons going down? What is that? 40 newtons up is positive. What about 100 newtons down? Yes, this one is going to be negative, exactly. All right, so let's go ahead. Sorry, my mouse is being a little bit crazy here. So let's go ahead and plug this in. So vertical force, we have first positive 40 going up, and we have second negative 100 going down. Now, don't give me the answer right now because that would be cheating. But just keep in mind what you're going to do is you're going to either think about this or plug it into a calculator, and you'll come up with your final answer, which you'll put here. Again, don't put it in the chat box right now, all right? Now, then we're going to go ahead and do horizontal force. So horizontal force, 60 newtons to the left, is that positive or negative? 60 newtons to the left, is that positive or negative? Yes, this one is going to be negative. And what about 80 newtons to the right? What is that? When it's going to the right, yep, it should be positive. So plugging this in, right, we end up with negative 60 to the left. We end up with positive 80 to the right. And again, you should be able to plug that into a calculator or think about it and come up with an answer. Don't put the answer in the chat box right now, okay? So there we go. So we've got that. Now, what we want to figure out is what's going to be the overall motion. So we can actually do this just by analyzing this picture. So taking a look at this picture, overall vertically, who's going to win, going up or going down? Which one's stronger, going up or going down? Who is going to win in the picture? Yeah, going down is definitely going to win, right? So going downwards is going to win. Now, on horizontally, left or right, which one wins? Left or right, which one wins? Yes, 80 newtons is stronger, so your right way is going to win. Okay, good. So we know that overall our vertical force is going to go down. Our horizontal force is going to go to the right. So now the object, can it go straight down and straight to the right at the same time? Can an object go straight down and straight to the right at the same time? Is that possible for an object to be in two places at once? No, so instead it's going to go between these and it's going to create what kind of line? Instead of going straight down or straight to the right, what kind of line does it create? It combines the motions to create what kind of line? Yeah, it creates a diagonal line, and that diagonal line, is it going up and to the left, up and to the right, down and to the left, or down and to the right? Which way should that diagonal line go? Yes, exactly, Antonio. This net force line is going to go down and to the right. So you should be able to describe this net force line over here and say it's a diagonal line. It's going down and to the right between the two net forces, between the horizontal and vertical forces. All right, smiley faces if that makes sense for this one. Again, I'm not writing out exact answers for you, and you need to be able to write them in complete sentences. I'm just writing notes for you up on the board. Awesome. 30 seconds to take a picture. Ready, set, go. Green checks, please. All right, I have 12 green checks, 44 of you. Please, moving on in 5 seconds. 3, 2, 1. Let's keep going. All right, question number 5 is asking about free fall. All right, so this one has to do with objects that are dropped, okay? So the acceleration due to gravity is 9.8 meters per second squared, okay? And we want to calculate the weight of a 500 kilogram object versus the weight of a 200 kilogram object, and we want to determine which one hits the ground first if there's no air resistance, okay? So weight is actually a synonym for the force due to gravity. So if we can figure out the force due to gravity, that is the weight of the object. And remember, forces we find by multiplying mass times acceleration, F equals ma. So what we need to do is we first need to find the mass of the first object and then multiply it by the acceleration due to gravity on Earth. So tell me in the chat box, what is the mass of the first object? What is the mass of the first object? So remember, mass is measured in kilograms. So we should be getting an answer with kilograms. And then we want to take a look at the first object. So I got an answer from Lola, I got an answer from Sarah. Do we agree? Do we disagree? What is the actual mass of the object? Remember, kilograms is our unit for mass, so what would this be? Tell me in the chat box. Yes, 500 kilograms is the mass of our first object, right? So in here, for this one, right, I would fill in that this is 500 kilograms, okay? Multiplied by the acceleration due to gravity. And what is the acceleration due to gravity? Keep in mind, units for acceleration are meters per second squared. So what's the acceleration due to gravity on Earth? Look up here at our problem. Yes, exactly. It is going to be 9.8 meters per second squared, right? That's our acceleration due to gravity. Right, so this is our AG. All right, so putting this down here, this would be 9.8 times 9.8 meters per second squared. I'm not even going to worry about that. Just put in the 9.8. So again, don't give me any answers, but what you should be able to do is you should be able to plug this into a calculator and figure out the weight or force in newtons of the first object. Okay, now you should be able to do the same exact thing with the second object. I'm going to guess that you can figure out how to find the mass of the second object. So if you know the mass of the first one is 500, you should be able to figure out the mass of the second one as well in kilograms. All right, smiley faces if you guys feel like you can figure that out on your own. Perfect, all right. And then multiply it again by the acceleration due to gravity. And the acceleration due to gravity, is this still the same or different? Is this acceleration due to gravity the same or different? What am I plugging in for AG? Yeah, it should be the same. So this still is 9.8. All right, so same thing, you would multiply those together and get the answer for the weight of the second object. Now the last question asks, what if they're dropped at the same height at the same time and only experience gravity? That means there's no air resistance working against them. Then let's think about this. This goes back to our video where we dropped a bowling ball and a feather in a vacuum where there was no air. And the bowling ball and the feather actually hit the ground what? Same times or different times? The bowling ball and the feather in our video, yeah, it was a really cool video, and we saw they actually hit the ground at the same exact time as long as there was no air resistance, and the only thing that was working was gravity. Exactly, Lissa, right? So what this means is that do mass and weight matter for how fast something falls? Do mass and weight matter for how fast something falls? Exactly. So these should hit at the same time because mass and weight don't matter. The only thing that matters is the acceleration due to gravity. All right, the AG, acceleration due to gravity. And the acceleration due to gravity is always what for both of these objects? Take a look at our equations up here. The acceleration due to gravity was always what? Because they're on Earth, the acceleration should stay that same, and that acceleration is always what? Yeah, so it's always 9.8. So if they have the same exact acceleration due to gravity, then they're going to fall at the same rate, because acceleration is the only thing that determines how fast they fall. Smiley faces if that makes sense for this one, and then I'm going to give you 30 seconds. Awesome, 30 seconds green checks for this one once you have a picture. All right, green checks please. I have 13 so far. Alexis, Amanda, Drea got yours. Andrew, Antonio, Ayandela, Ben, Cameron, Candace, Kayla, Chloe, Christian, Chris, Dajane, Diego, Enrique, green checks please. Enrique F. Erwin, Isaiah, Jalen, Jazz, green checks please. Jose, Joe, Kayla, Waiting on Nani, Kirsten, Lolo, green checks, MJ, Michael, Ray B, Ray C, Tatiana, Trent, green checks, everyone. All right, let's keep on going. Oh wait, so question number six is asking about density and buoyancy. So remember, the density of water is 1 gram per milliliter. And we want to remember what happens depending on something, if something is more dense, less dense, or the same density, okay? So let's think about this. If an object is more dense than the density of water, then what's going to happen to it? Oh, sorry, I've been talking and you couldn't hear me. Sorry. As I was saying, if the density of water is 1 gram per milliliter, what's going to happen if something is heavier or is more dense than the density of water? What happens to objects that are more dense? What happens to object with a higher density? Yeah, a higher density object is going to sink. Exactly. It's more dense. That means that the molecules are closer together, and so they're heavier for the amount of space they take up, and so they sink. What if it has a lower density? What happens to an object with a lower density? If it has lower density than water, yeah, then it's going to float, exactly. And what if it has the same exact density? What if it has the same exact density? Yes, it will be suspended in the water, exactly. So something with the same exact density will be suspended in the center of the water. Awesome. So what you want to do is you're going to take a look at these three different objects, right? A regular soda can has a density of 1.07 grams per milliliter. Is that more or less than the density of water? Is 1.07 a bigger or smaller number than the density of water? Yeah, this is definitely more, right? So that should help us figure this out, right? So this one is definitely going to be a higher density, and you should be able to figure that one out. Okay, you should then be able to figure out a diet soda, right, has a density of 0.93, a rock has a density of 1. So you should be able to figure out what happens to these based on our notes up here, okay? Now the last question asks, if we add a ball with a density of 0.57 grams per milliliter, what percentage of that ball goes under the water surface, right? And so not all of it sinks, but we want to figure out how much of it does end up underwater. And this is like ice. Remember we talked about ice has a density of 0.97 grams per milliliter. And all we had to do to figure this out is just change 0.97 into a percentage. So what would this percentage be for ice? Okay, we're not doing the ball because that would be giving you the answer, but we can do ice. What would be the percentage for ice that goes underwater? If we just turn that into a percentage. Tell me in the chat box. Turn 0.97 into a percentage. What does this percentage become? Yeah, exactly, 97, right? So you literally just turn it into a percentage, and so what we know is when we turn it into a percentage, 97% of it sinks underwater. Okay, so that's why an iceberg, only 3% of it is above water, and most of an iceberg is actually below the water surface. Okay, so in the same way, you should be able to just turn this into a percentage and figure out how much of that ball will be under the water surface versus how much is above the water surface. All right, go ahead, take 30 seconds, give me a green check when you have a picture of this, and go. All right, green checks if you're good, red X's if you're having any problems. Otherwise, I'm going to move on. All right, I'm only seeing green checks. I'm moving on. Perfect. Okay, question number 7 is now asking about pressure and what happens to pressure and objects in different scenarios and why. So first, let's go ahead and start off with the air in the balloon. So the air in the balloon that is left outside on a winter day. All right, so a winter day, does that mean it's cold or hot? What does that mean for our temperatures? On a winter day, is that going to be a cold day or a hot day? Yeah, so we have cold temperatures, right? So we want to know what happens with cold temperatures. So what's going to happen with our molecules? If they're cold, are they going to move faster or slower? Molecules, are they going to move faster or slower? Yes, they're definitely going to move slower. And if molecules are moving slower, what do you think? Are they going to run into each other more or less? More collisions or less collisions? Yes, we're going to end up with less collisions, and less collisions, right, means less pressure. Right? And if that happens, if there's less pressure on the sides of that balloon, what do you think is going to happen to that balloon? Is it going to stay the same size? Is it going to inflate, deflate? What do you think? What's going to happen to that balloon as the pressure goes down? You can actually experience, if you ever blow a balloon and put it in the freezer, you can actually see this happen after like an hour. What's going to happen to that balloon? Inflate, deflate, stay the same. Hello, can you hear me? What happens to a balloon if it's losing pressure? Less pressure, is it going to get bigger and inflate or get smaller and deflate? Yeah, exactly, Wes. It's definitely going to deflate, right? It's going to get smaller. Cool. What about, let's see here. The next one is an air pressure in a closed water bottle that is being twisted to make it smaller. So smaller means we have a smaller volume. And if we have a smaller volume, that means we have less room to move around. So for those molecules, if they have less room to move around, what happens to the collisions? More collisions, less collisions. If they have less room to move around. Less room. Yeah, you're absolutely going to end up with way more collisions. It's like stuffing everybody into a locker room, right? So you should be able to think about more collisions, therefore what happens to pressure. And if you keep on doing that, twisting that bottle cap, or bottle, what's going to eventually happen to the bottle cap? What's going to eventually happen to the bottle cap? Yeah, exactly. So the cap's going to pop off, right? Awesome. What about gas pressure in a propane tank? So propane tank, what's happening to the temperature of a propane tank if it's being accidentally heated up by a nearby fire? What's happening to the temperature? Is it getting colder or hotter? Yeah, so this is hot temperatures. And so we should be able to think about this as being the opposite of cold. So you should be able to think about molecules move what? You should think about what therefore happens to collisions and therefore pressure. And then you should also be able to think about what could happen to the, yeah, so right, it's gonna blow up. Absolutely. All right, so I'm not gonna give you those answers again. We should be able to do that on our own. And what about a bike tire? So a bike tire, we're blowing it up, we're pumping it up. So if we're pumping up a tire, are we adding air molecules or removing air molecules? If we're pumping up a tire, are we adding more air molecules or subtracting? Yeah, we're adding. So we're adding more air molecules. And in this case, right, we want to think about if we're adding more molecules, are they going to start running into each other more or less? Think about a gym where we add 500 more people. What's going to happen? More collisions or less collisions? Yep, exactly. So you should be able to think about more collisions and therefore what happens to pressure. And then you should be able to think about, is this tire going to inflate, deflate, deflate, or stay the same? All right, go ahead, take a picture of this. Give me a green check when you have it saved. And then we still have a couple more. I know we're going to go a little bit over time, but I want to make sure we get through all of them. Go, go, go. Green checks. All right, let's keep on moving. Question number 8. Question number 8 asks about Bernoulli's principle. Again, if you were not here or if you did not watch yesterday's video, you need to make sure that you get it done because yesterday's video is all about Bernoulli's and Pascal's, and so it'll make a lot more sense once you watch yesterday's video. But it asks about what's occurring to air molecules as they move faster above an airplane and how does this affect pressure? What about the air molecules below, slower underneath the airplane? And then how do these differences affect the wing? Okay, so let's think about this. If air molecules are moving faster, do you think they're going to get closer together or further apart? Think about if you're running, right? Do you want to be close to people or far apart from people? If you're trying to run, do you want to be closer together or farther apart? What's going to happen to these molecules? Yeah, exactly. So molecules that are moving fast actually spread apart. And if they spread apart, do you think there's going to be more collisions or less collisions? Again, think about why would molecules want to move further apart if they're moving really fast? Are there going to be more collisions or less collisions? Yeah, we're going to actually end up with less collisions. And so you should be able to think about what therefore happens to the pressure. Remember, pressure and collisions are the same thing. Now, same thing with molecules that are moving slower. Are they going to be more spread apart or closer together? If they're moving slower, think about people that are walking. Are they going to be more spread apart or closer together? Yeah, so these ones are going to be closer together. And so same thing, you should be able to think about what happens to collisions and therefore what happens to pressure, because pressure and collisions are the same thing. Now, the last thing to think about is that what ends up happening is with an airplane wing, you end up with a lot more pressure underneath the wing. So you have more pressure pushing up and less pressure on the top pushing down. So if we have more pressure pushing up underneath, what do you think is going to overall happen to the net force on the wing? If more pressure is going up, what overall is our net force? Up or down? If we have more pressure overall, if this is our wing, and we have way more pressure on the bottom, and much less pressure on the top, what overall happens? Yeah, overall, it's going to go up. So our net force is up, and that net force is what we call lift. So this net force is called lift, and so the wing is able to go up. Wing goes up in order to fly. All right, take a picture of this green checks, 30 seconds, and then we just have 2 more. Thanks for staying, guys. I know we're almost done. Sorry, I cleared them out. Green checks again. Go, go, go. 5 seconds, green checks. Moving on. All right, here we go. Question number 9 is asking about the pressure of a 600 Newton person standing on a carton of eggs with their foot in contact with the surface area of 0.04 meters squared. So the cool thing about this is when you actually stand on a carton of a dozen eggs, you can actually stand with your foot on it and not break any of the eggs. All right, it's really cool. This is why people can also walk on nails, for example, or lie down on nails. Smiley faces if that makes sense. Okay, so they're walking on a surface with 12 eggs. Okay, and the surface area ends up being 0.4 meters squared. Okay, now if you take that same person though and you put them on a single leg, that single leg is only in contact with a surface area of 0.003, which is much, much, much smaller. Okay, so then we want to explain why does the person crack the single egg but does not crack the carton of eggs. Okay, so what we want to do is we want to calculate pressure first. So pressure, remember, is force divided by surface area. So what is the force or weight of the person? Tell me in the chat box, look up here again, what is the force or weight of the person? Yeah, it's 600 newtons. All right, so this is actually going to be true for both of the top and the bottom. Right, so for both of these, the person weighs the same. So the force is still 600 newtons. But for the carton, what is the surface area that the person is stepping on the dozen of eggs, the carton of eggs? What's the surface area for the carton? Yep, exactly, Wes. It's 0.04 meters squared. Awesome. Versus the egg, a single egg, what is the surface area of the single egg? What is the surface area of just the single egg? The entire carton is 0.04 meters squared. What is a single egg's? Take a look at our second sentence here. What is the surface area of the single egg? Awesome, Drea. Yes, it's 0.003. Okay, so for both of these, don't give me answers right now, but you should be able to calculate these, and you should end up with some pretty big numbers, okay? So you should, again, make sure you do 600 first, and then divide by 0.04. And then do 600 first and divide by 0.003. Okay, and make sure you enter these correctly so that you get the correct answers. Now, what you should find is the pressure on the single egg should end up being much, much, much bigger, because what's happening is we're taking all of that force and putting it into a single point. And if you put all of your force into a single point, just like our high heel example, do you think that's a lot of pressure or very little pressure? Tell me in the chat box. All of that force, all force on a single point, what's going to happen to our pressure? Big pressure or small pressure? Yeah, it's going to be a lot of pressure, right? Lots of pressure, kind of like a high heel. Lots of pressure, kind of like a heel. Okay, so that should help us answer this last one right here. So give me a green check when you have that saved, and then we just have question 10 to talk about. So go ahead, work quickly, green checks. 3 seconds and we're moving on. All right, so our very last question asks about Pascal's principle. All right, and so if we remember back to yesterday's video, Pascal's principle says that when you try to increase pressure on a single point in an enclosed fluid, okay, this actually increases pressure the same amount or uniformly everywhere else in that fluid. Okay, so again, don't just copy this because this is not a complete sentence. So make sure that you actually either watch yesterday's video to figure out what the complete definition is, or you change this into a complete sentence. Okay, so that's what Pascal's principle is right here. Now, based on this, it wants us to figure out what's the input force versus the that's needed to lift the car in this diagram. And again, I have an entire example of this in yesterday's recording. So if you're not sure exactly what I'm talking about, make sure you're watching yesterday's recording and you're taking a look especially at this slide. Okay, so what this means is that if pressure increases the same everywhere within a fluid, that means that the pressure on the input side of a hydraulic lift is actually the same as the pressure on the output side where we're actually lifting the car. Smiley faces if that makes sense. So the pressure of input is the same as the pressure on the car based on Pascal's principle. Okay. Now we already know what the equation for pressure is. So we can, instead of saying pressure of input, we can just put it as the force of the input divided by the area, because that is pressure. And same thing for the car. We can just say the force of the car divided by the area of the car, because that's the same thing as saying pressure. And these things we actually know. So what is the input, what is the area on the input side? Tell me in the chat box, what is the area on the input side? Yep, 1.5, awesome. And what is the force of the car or the weight of the car? Remember, force of the car and weight of the car are the same thing. Yep, 2,500 newtons. And what's the area that the car is on? What is the area of the hydraulic lift on the car side? Yeah, 50 meters squared. Awesome. So what you would be able to do is you're not going to do anything on the left first because you can't simplify that any further. But on the right, you should be able to simplify what 2,500 divided by 50 is. So what you would first do is you're going to go ahead and first plug those in and calculate what's 2,500 divided by 50. Don't give me an answer now, but that's what you would put in here. And then lastly, to get rid of this dividing by 1.5 on the left, we need to do the opposite. And what is the opposite of dividing by 1.5? What is the opposite of dividing? Tell me in the chat box. What is the opposite of dividing? Yeah, multiplying. So we're going to multiply by 1.5 on the other side. Okay, so what this is going to do is it's going to get rid of the 1.5 on the left, right? 1.5 on the left, we'll get rid of that. And on the other side, we just multiply by 1.5, and that should give us our final answer. Times 1.5. Oops, sorry. Let me clear that up a little bit. So on this side, all we would do is we would take our answer that we just got, and we would multiply it by 1.5. All right, and that's going to give us our final answer right here. That's just some simple algebra, okay? And then we want to figure out, will this make lifting the car easier or harder? So if we end up with a smaller input force, this should make it easier. If we end up with a bigger input force, that would make it harder, okay? But hopefully you should be able to figure out a hydraulic lift, should it be making your life easier or harder? All right, go ahead, take a picture of this. You have 30 seconds, and then I'm going to give you your end of class word. All right, green checks, everyone. All right, so make sure you complete your 4D exam. The recording will be up in about half an hour, so if you want to wait until the recording's up, you can totally do that. Just make sure to try to get it done today, and that will get graded over the weekend as well. And I'm still working on the lab, so those will be finished over the weekend too. All right, so I'm going to go ahead and stop our recording,